Okay. So, today we will discuss the a basic topology on the set of real numbers, and first we will discuss what is one correspondence, then we will go for the countable and uncountable concept of the countable and uncountable sets. The two sets A and B are said to have one-to-one are said to be in one-to-one correspondence, if there exists a one-one mapping from A onto B. And then if A and B are finite, then we say the cardinality of A and cardinality B is the same. If A and B are finite sets, then the cardinality or cardinal number of A is the same as the cardinal number of B. But if A is infinite, then there is no sense of talking the number of element in the set both. So, in that case, when A is in B are infinite set, then instead of saying the cardinality is the same, we say they have a one-to-one correspondence. That is more meaningful than saying the numbers are same. Okay. So, this is one. And the relation which we have, if we put the relation, suppose A is rated to be if A is a one-to-one correspondence, to B, then this relation is obviously is reflexive, symmetric and transitive. So, it is a equivalence relation. So, it is an equivalence relation. So, we also say, we can say that A is equivalent to B. When A is one-to-one correspondence to B. So, that is the way we define. Now, using the concept of the one-to-one correspondence, we can now define the finite set, infinite set, countable and uncountable set. The definitions is for any positive integer, say n, let J n represent the sets having the element 1, 2, 3 say up to n. The first n in natural number of positive integers, and let J is the set of all positive integers 1, 2, 3 and so on. This is the set of all positive integers. Okay. Then for any set A, we define, we say A is finite, A is a finite set, if A is equivalent to J n for some n. Obviously, once it is equivalent to some n, then n is fixed. So, J n is finite, the number of the terms is n only. So, A will also be finite, one to one correspondence, and the set will be a finite set. Empty set in particular considered to be a finite set. So, in particular empty set phi is considered to be finite. Then a set B, a set A is said to be infinite if A is not finite. In fact, this definition we can further modify it, and we get a better way of defining the infinite set as in the next next part when we discuss about countability. Okay. So, A is finite means if it is not infinite, A is infinite means if it is not finite, and see A is countable if A is equivalent to J, that is there is a one to one correspondence between the elements of A and the J, or we can define a mapping from set of positive integer to A which is 1 1, then such a set A is said to be a countable set. Okay. So, this J we have though started from 1 to n, 1 to infinity, we can also take J from 0 1 to n, with starting the point x 0 0 corresponding the point x 0, x 1 corresponding to point x 1 and so on. So, we can also consider the positive or non-negative integers, including 0. Okay. The A is uncountable, A is said to be uncountable if A is neither finite nor countable, and E we say A is at most countable, if A is finite or countable. Finite set is also a countable set, but if the set is finite as well as and also count means finite, that set will be considered countable. Countable set itself is countable. So, we say A is almost countable means either is finite or maybe a countable set. That is what countable. The countable set also known as countable sets are also known as denumerable set, denumerable or enumerable sets, all numerable sets. Okay. Let us take some examples where this we say let A be the set of all integers, A be the set of all integers. Okay. Then set of all integers, B claim that this set of integers A is countable. We claim A is countable, it means we are able to define a one to one correspondence between the sets of positive integer and the set of the elements A. So, let us define a mapping F from the set of positive integer j to A as follows. If I take the image of any n under F is say n by 2 if n is even integer, even positive integer, and otherwise when we say n minus 1 by 2 if n is odd positive integer. So, what we see here is that if we take A, which is the set like 0, 1, minus 1, 2, minus 2, 3, minus 3 and so on, and J which is the set of positive integer 1, 2, 3, 4, 5, 6, 7 and so on. So, what he says is as soon as n is even, it will give n by 2. So, this is related to here. Okay. Then 4 will go to here, 6 will go like this, and when n is odd, then you are getting this thing, this thing, and of course, 1 will go to 0. So, there is a 1-to-1 correspondence between the elements of the set A and set J. So, obviously, this and this mapping is 1-1 mapping. 1-1 mapping we can just check it, because F is 1-1 means f of x 1 equal to f of x 2 should implies x 1 equal to x 2. So, here if it say n is even, then obviously, when you take f n 1 equal to f n 2, obviously, n 1 comes out to n 2. Similarly, here when n is odd, we are getting same. So, obviously, f is 1-1 here. So, that is why this set of positive integers is a countable set. One more thing which we can see here is a remark. What we have seen is that this A is a set of integer, but J is a set of positive integer. J is a proper subset of A. So, but they are having a 1-to-1 correspondence. So, what we can say is what we conclude or we observe here is, in case of the infinite set, we can say A is infinite when A is equivalent to one of its proper subset. In case of infinite set, a proper subset may be equivalent to the set itself. So, in case of infinite set, a proper subset A is equivalent to, in case of infinite set say A is equivalent to one of its proper subset. And this is also a way to define a infinite set. We say a set is infinite if A is equivalent to one of its proper subset. So, we say, and that is A is infinite, set if infinite set if A is equivalent to one of its proper subsets. That is what. Okay. Now, another remark we can put it here, that every elements of any countable set can be arranged in the form of the sequence. Elements of a countable set elements of a countable set may be arranged, can be arranged in a sequence, because basically what we have a 1-to-1 correspondence with this set of positive integer. So, corresponding to 1 we are getting x 1, corresponding to 2 we are getting x 2, corresponding to 3 we are getting. So, this form basically sequence, because it is like this. if A is any set having the elements here, these are the elements for this set A, okay, then J is what? J is 1, 2, 3 and so on. It has a 1 to 1 correspondence. So, corresponding to 1 you are getting x 1, corresponding to 2 you are getting x 2, corresponding to 3 you are getting x 3 and so on. So, this has a 1 to 1 correspondence with this, is it not, like this. So, we get the 1 to 1 correspondence between the set of positive integer and the elements of the set. So, element of a countable set can be arranged in the form of the sequence. So, this is also a remark which we can use, we will use it. Now, this is a interesting result, and result says every infinite subset of a countable set A is countable. Okay. So, proof is, let E be an infinite set, let E be a subset of A and E is infinite. E is infinite. Now, since A is countable, so we can arrange the element of A in the form of sequence. So, A will have the sequence like x 1, x 2 and so on. All the elements of the set can be arranged in the form of the sequence. Okay. Now, let us construct a sequence. Construct a sequence n k of positive integers as follows. Suppose n 1 be the smallest positive integer, be the smallest positive integer such that x n k, x n 1 is an element of E. Means from this n 1 to 3 and so on, suppose I am taking the n 1, n 1 is the smallest integer. So, that the first x n 1 corresponding to this x n 1 is an element, means out of this the first element which you are getting is x n 1 belongs to E. Then assume that n 1 choosing n 1, n 2, say n k minus 1, where k is 2, 3 and 4 so on. These are the after choosing in such a way when n 2 is greater than n 1 and such that x n 2 belongs to E and so on. Let us take n k now be the smallest integer, be the smallest integer, with the smallest integer such that be the smallest integer such that n k is greater than n k minus 1 and the corresponding term of the sequence x n k belongs to E. Okay. So, now let us introduce the function f from j to E. So, if we take f of n as x of n k, f of k, let us take f of k as x of n k, where k is 1, 2, 3 and so on. Then what we see here, there is a 1 to 1 correspondence between j and E, because for k is 1, x n 1 is in E, k is 2, x n 2 is in E, x n k is in E and like this. So, this is a 1 to 1 correspondence between E and J. Hence, E is countable. Hence, E is countable. Okay. So, this shows that every infinite subset of a countable set is countable. Okay. Clear? Is it okay? So, this one. Now, here as we have seen that if A is countable, we can put it in the form of a sequence x 1, x 2, x n, all the elements we can arrange in the form of the sequence x 1, x 2, x n. If I generalize it, say why, because 1 to n is basically set of positive integer. So, instead of this we can take the collection family of the sets also. So, we define like this, let A and omega be sets, and suppose with each element alpha of A there is associated a subset of omega which is known, and suppose for each element alpha belongs to A, alpha A, there is associated a subset E alpha of omega, subset say E alpha, subset denoted by E alpha of omega. Okay. Then the collection of all these E alpha, then this collection E alpha where alpha belongs to A, this collection alpha is the collection of the sets, is the family of the sets, or subsets of Q, subsets of omega, family of subsets of omega. Now, if we take S as the union of E alpha when alpha belongs to A, then this for at least one we used, then any element belongs to this means it will be in one of the alpha E alpha like this. So, for at least one alpha we used it. Okay. And in particular when A is an positive integer, A is the set of positive integer, then S becomes union E m, m is 1 to infinity, and this we say it is a countable union of E m's like this. So, even similarly for the intersection also we can introduce. So, this will be needed, so we can just define. Now, let another results in the sequence of the countable sets. Let us suppose E n and n is 1 to n so on be a sequence of countable sets, and put and let S is the countable union of E n. S is the countable union of E n's, n is 1 to infinity. Then what we claim is that S is countable, then S is countable. So, a countable union of a countable set is countable, that is what this result says. Okay. Now, what is E n? E n's are given to be countable. So, it can be arranged in the form of the sequence. So, proof is since E n for each n, since E n for each n is a countable set, so its elements can be arranged in a form of the sequence. in the form of sequence, in the form of the sequence, say x and k, where k is 1, 2, 3 and so on. K is 1, 2, 3. It means that is E1 set E1, we can arrange the form for the set E1, we can arrange the elements like this: x 1 1, x 1 2, x 1 3, x 1 4, x 1 5, x 1 6 and so on. For E2, the elements, suppose we are arranging x 2 1, x 2 2, x 2 3, x 2 4, x 2 5 and so on like this. And ENs, suppose we are arranging x n 1, x n 2, x n 3, x n 4, x n 5 and so on like this. So, continue this. Okay. Now, let us consider the following array. Consider the array as mentioned above, infinite array as shown above by arrow. What is this? Suppose I take this arrow first. Let us take this another pen. Then suppose I take this as first element, this ray. Then I choose this one. Then I take this arrow. Then I take this one, x n 1, x n 2, x 3 1. Oh, sorry, this is like this. Okay, x 3 1, x 3 2. So, basically this will be the x 4 1, this is x 4, it is wrong. So, this will be x 4 1, x 4 2. So, this ray will go, this ray will go, okay, not this, like this. So, if we continue this way, that is what we are doing is we are taking up this ray like this. The first element we are choosing x 1 1, the first array, then second one I am taking as x 2 1, x 2 2, x 1 2, then third ray we are taking as x 3 1, x 2 2, x 2 2, x 1 3, x 1 3, and fourth one is say x 4 1, x 3 2, and then x 2 3, and then x 1 4, like this. Continue this. So, if we arrange this in the form of the sequence, then what we get is we are getting first element, second element, third element and so on like this. So, in this way we are getting a one-to-one correspondence between the elements of this set and set of positive integer. It may so happen that some of the elements of this sequence may be repeated. Then what we can do is we can get the subset of this set. Since it is an infinite subset, so subset of this we can find out integers, subset of t, integer j, which is also countable. So, with that it will be a one-to-one correspondence. We drop this common element and make the correspondence with the set of positive integer. So, if any two of them, if any two of the sets E n have elements in common, then these will appear more than once in this arrangement. In this arrangement, say star, in this arrangement star, then what we say, hence there exist hence there is a subset of T of the set of all positive integers, T of the set of all positive integers such that S and T, which S is equivalent to T, which shows that S is at most countable. That S is at most countable. Let us see what is the meaning of this. Once we have arranged this union of this S n E1 E2 n, this each E n we are arranging in the form of the sequence. So, now take the array like this. So, choose the element, first element 1 1, then second element x 2 1, third element x x 1 2, fourth element may be the x 3 1, then x here x 3 1, and this will be the x 3 1, then this array where the sum is 4, Okay. So, this one and continue. So, this has a 1 to 1 correspondence with the set of positive integer. In case if suppose some elements are repeated, then what we do? We just drop that elements, take only once. So, that will be have a 1 to 1 correspondence with this subset of J, that is there will exist a subset T of the set of positive integer, which has a 1 to 1 correspond with this set of elements of S. So, S becomes countable. Okay. Now, S may be finite or may be infinite. So, but S cannot be finite. So, we can take it to be the let us why, because since E1 which is contained in S, because S is the countable union of these E n's. So, E1 is contained in S and E1 is given to be infinite, and E1 is infinite, because this is already given that sequence of countable sets E n's is the sequence of the countable sets which are infinite, of course, each element, then E is one infinite, then S will be infinite. So, this shows S is countable, this implies S is countable. S is countable, and that is prove the result. Okay. So, this is our okay. Same results we can generalize it. So, as a corollary we can say suppose A is at most countable, countable, and for every alpha belongs to A, B alpha is at most countable, which is a subset of omega, of course, at most countable. Then T, which is the countable union of B alpha when alpha belongs to A is at most countable. At most countable means either it will be finite or infinitely countable or infinitely countable. Okay. So, that is another results which we in this sequence we have. Let A be a countable set, be a countable set, and let B alpha B n V the set of all n tuples set of all n tuples of the say A1, A2, An, where A k is these h elements, they are the elements of A, k is 1, 2, say up to n, and the elements A1, A2 need not be, and the elements A1, A2, An need not be distinct. Then Bn is countable. So, what this theorem says is that if we construct a set B or Vn, that is Bn is the set of all n tuples A1, A2, An, where A k's are in A. Now, if these coordinates of this n tuples belongs to a countable set, then this collection of all n tuples will also be a countable set. That is what he says. So, in particular, when you take n equal to 2, the ordered set of all ordered pair, where A1, A2 belongs to a set which is countable, then this set of for n is 2 becomes countable, and this will give leads the proof for the rational number to be countable. So, let us see the proof of this first. This will be proved by induction. So, what is our B1? For n is equal to 1, B1 is basically only single element A1. It means B1 coincide with A, but A is given countable. So, once it is countable, so this implies that V1 is countable. So, let us assume that up to Bn minus 1 is countable. So, let us assume let B1, B2, Bn minus 1 is countable set. Okay. Now, we will prove for n Bn. So, consider the Bn. We can put it Bn in the form of ordered pair B A, where what B? Where B belongs to Bn minus 1, a tuples where B is B1, B2, Bn, Bn minus 1, and then comma A, nth term is A. So, B1 and n in A belongs to A. Okay. Clear? Now, if I fix B, then once you fix up B, it means each element of A, we are combining with B, that is all. So, basically you are getting A itself, is it not? So, that is nothing but, so for every fixed B, the set of pair, the set of pairs B A is equivalent to set of B A is equivalent to A, but A is given to be countable, hence countable. So, thus Bn is countable. Okay. Thus, Bn is countable. Union of Bn is union of a countable set, is a union of a countable set, because A is countable and this you are fixing Bn minus 1, which is also a countable. So, basically Bn is the union of the countable sets Bn minus 1 and A. So, it is hence it is countable. By the previous result. Therefore, B n is countable. So, this proves the theorem. Now, as a particular case I told that when you fix up the n is 2, then we get the very important result that all set of rational numbers is countable. The set of all rational numbers is countable. Why? What is our rational number? The set of rational number q is basically of the form say b by a, where a and b are integer, a is not equal to 0 and the divisor of this is 1, means they do not have a common factors in it. Okay. So, this is 1, even if it is not 1, even if we do not put it, say 2 by 4, 1 by 2, we can take also that one. So, this is all general in this form a by b. Now, what is this? This is basically an ordered pair, say b a, where the order is a b by a. So, a is an integer, b is also an integer and both are countable set. So, basically it is a union of the countable sets. So, in the previous theorem, if we take n is equal to 2, then this shows that q is countable, because b is in I, which is countable, a is in I, which is also countable. Therefore, it is countable. So, set of all. Now, this we will just give an example, but we will show it later. Exercise, which is we will prove it now. Set of all algebraic numbers set of all algebraic numbers is a countable set. Second, we can show we will prove that this I am leaving an example, but otherwise next we will show it also when it is okay. Set of all, that is okay, all these infinite real numbers, set of real number, or okay, set A, of all sequences, set A of all sequences whose elements are digits 0 and 1. All digits 0 1 is uncountable set. So, in fact, this result shows, the second example shows. So, this example shows that all these infinite set need not be countable, that all infinite sets need not be countable. In fact, we will show that set of real number is not countable, set of rationals are countable, set of irrational becomes uncountable set. So, let us see the result, the theorem which is formed in the form of theorem, proof of solution for 2, or this you can also say in the form of theorem as a let us suppose E be the countable subset of this. Okay. Let given A be the set of all sequences whose elements are elements are, say, whose elements are like this, all the infinite sequences, all the sequences, set of all sequences whose elements are digits 0 or 1. That is, A will be a set of this type of sequence, say 1 0 1 comma 1 0 comma 0 like this, or maybe 1 1 1 0 1 0 like this. Means all these sequences, infinite sequence where the digits are either 0 or 1. We claim that this set will be an uncountable set. So, let us suppose E be a proof. Let E be a countable subset of A. Let us suppose let E be a countable subset of A. Let us take this. Okay. Okay. It means every E can be arranged in the form of sequence. So, let E consist of the sequences, E consists of sequences, say S 1, S 2, S n, S 3 and so on, because this is countable. So, we can arrange the elements in the form of this. Now, each S 1, S 2, S n, where S I is this, maybe 1 0 1 1 0 0 0 and so on, means digits are either 0 or 1, digits 0 or 1, each is I will get. Now, from this let us construct a new sequence S. So, construct a sequence, S as follows. What is the way we are constructing sequence is that if the nth digit in S n, if the nth digit in S n is 1, then we let the nth digit of S be 0 and the vice versa. Means what, how we are choosing is, suppose S 1, S 2, S n is given sequence. So, I am constructing a sequence S such that if the nth digit of S n is 1, then we will replace 1 by 0. It means the first term of this term we will look the S 1. If the first term in S 1 is 1, we will get it 0. If first term in the S 1 is 0, we will take it 1. Similarly, for second term of S 2, we look the for second term of S, we look the sequence S 2 and see what is the digit. Whatever the digit there, we will take the just opposite of, means if it is 1, we will take 0, if it is 0, it is 1. It means the sequence S so obtained will differ from all the terms of the of this this set E. So, obviously, so what we see here is that the sequence S differs from every member of E. In at least one place, because we are constructing in such a way. So, once it is differing from each element and E is already countable, we have arranged the term in the form of sequence S 1, S 2, S n, and since S is not coinciding with any one of the term. So, this implies that S is not an element of E. It means what? But S is what? But S is an element of what? A, because A is the collection of all such sequences whose digits is either 0 and 1. So, E is a proper subset of this. This implies E is a proper subset of A. Subset of A. Okay, E is a proper subset of A. Okay. And once we have already shown, and it is known, or it is shown that every countable subset, of A is a proper subset of A, is a proper subset of A. Every countable subset of A is a proper subset of A. This we have shown already. Every countable subset of A is a proper subset of A. So, A cannot be countable, because as soon as A is countable, then the subset which you are getting must be proper. So, this implies that A cannot be countable, because if A is countable, then here itself we are getting a contradiction, is it not? Because otherwise A would be a proper subset of itself. Otherwise, A would be a proper subset of A itself, would be a proper subset of A itself, which is absurd, because a set cannot be a proper. A set will be a subset of itself, but cannot be a proper subset. And here if we assume A to be a countable, then it must be have a proper subset. So, this is every proper subset must be, but here we are getting that this cannot be a count. So, this shows that A is uncountable. This shows A is uncountable. A is uncountable. Okay. So, this is a thing. Now, one more examples which we will deal is set of a number countable and other. Okay. Let us take the few more, that is this example, as we have seen, the interval 0 1 set of real numbers is not countable. Now, this we will prove it by using the decimal expansion. Suppose I take x any element of R, we can arrange this in the form of the sequence, say x is in R, then we can write it, we can represent x in the form of in its decimal expansion. We can write the decimal expansion for this. So, if x is something alpha 1 point, say a1, a2, an and so on, then this a1, a2, an, and these are numbers different from 0, 8 and 9. Okay. So, in order to repeat the whole 9, and then what we do is we can construct the another numbers, say first press a1, we can replace it by a number which is not available here. Just change it, just like a previous thing we did it. As we have constructed sequence where we have replaced the first element of the sequences by looking the S1. If it is 1, we will take 0, if it is 0, it is 1. So, similarly, here also we looked at and then replace it by a number which is not out of this. So, that at least each element will differ from the constructed one. So, we will say it is not. I will complete this thing next time. Thank you very much.